Hello, our group name is Cooler Kids, and our focus is on studying PC fan cooling and airflow. My name is Luke Brosell.
My name is Colin Haggett.
My name is Asa Myers.
And my name's Corbin Ward.
First, we'd like to propose a question to you. Why do fans have the number of blades that they do? We'd like to answer this question by performing some tests on computer fans with differing numbers of blades. By seeing which blade count results in the highest airflow for a common design geometry, we hope to determine an optimal number of blades for cooling performance. This would also allow us to see if the number of blades on the stock unaltered fan we will be using could be increased or decreased to reach higher functionality. A test we will run in parallel will allow us to see the actual cooling performance of our test fans by measuring the heat dissipation over a radiator connected to a loaded CPU. Computer components such as CPUs and GPUs can get extremely hot under stressful loads, with some hotspots reaching temperatures of around 90 degrees Celsius. This can be a bottleneck for how quickly machines can run computational tasks and needs to be dealt with. PC fans and cooling systems are crucial to attaining the best performance from your computer. The optimization of singular fan blades by changing parameters such as blade pitch, cord length, or blade camber has been overdone. In this way, certain design types have been pretty well standardized across the PC market. However, not much has been done to study the impact of blade count on fan performance. We believe that this parameter is just as important when looking to achieve the best airflow and cooling capacity as blade geometry. In this way, our project takes a different approach in the quest to improve fan and computer efficiency. None of our group members have done any previous work with computer fans or fan design, so this is all a little new to us. We found it would be too hard to simulate our expected results using our giving tools and thought it better to just obtain our results directly.
Before starting, we looked at the current research available to determine how others optimize fan blade counts in other research settings. There's not much research on axial PC fans, so two of the other places looked at were optimizing ceiling fans and centrifugal fans. For ceiling fans, they were modeled on computer software with a range of blades from 2 to 6. They looked at volumetric flow rate, torque, and energy efficiency, and they found that the most efficient was the 2-blade design, while a 6-blade design had the highest flow. The other major research looked at was the design optimization of a centrifugal fan. A centrifugal fan works by pulling air from the center and pushing it out to the side. Their computer simulations found that 20 blades was the most efficient. While both of these pieces of research were helpful, they were both different in a few key ways. The most important difference was that they were both modeled on a computer. The other difference is the type. While a ceiling fan is similar, it is not the same as a small PC fan. And while a centrifugal fan shows up in laptops quite often, it works on a different principle, and optimization of that type is different from that of axial fans.
We expect our test results to have a mostly economic impact. Cooling systems for large data centers account for between 30 and 55% of a center's total energy consumption. This contributes heavily to the operational expenses for a facility like this. By even marginally improving the cooling efficiency of the fans used, a great deal of money could be saved. Besides this, PC enthusiasts may be willing to pay more for a product that allows their system to reach higher performance. By knowing the best number of fan blades to use, companies could develop better products that allow them to achieve higher margins.
One of the many ways to determine fan performance is through calculating the volumetric flow rate through the fan. We were lucky enough to have been provided an Alienware R16 desktop by Professor Hoover, and we decided to base our testing off of this. CPU in the computer is liquid cooled and has a 5-bladed 120 millimeter fan on the cooling radiator. We were able to disassemble this fan and found that the hub uses a magnetic ring inlaid in the center that allowed the fan to spin alongside a small metal pin that stabilized the fan in order to prevent the fan from shaking and vibrating out of control. With these two pieces, they were able to make the fan operate in a smooth fashion. After the components were taken out of the fan, we were able to take the measurements and model the fan in SOLIDWORKS. The fans were designed by modeling a single blade and using SOLIDWORKS' circular pattern function, so each blade is equidistant from each other for each blade count. The blades were printed using a combination of 3 printers in Professor Hoover's lab, as well as the generosity of Tom. The printers in the mechanical engineering lab were fussy to run, but we were able to get them all working. However, with the time crunch created by the blades being orientated in the wrong direction, Colin stepped in and printed some from his house. Now that we have the blades, we still need to find a way to test them reliably. The computer that Professor Hoover gave us has pre-installed motherboard control center that allows the user to manually adjust the fan's motor speed. Another function of the program is the ability for it to monitor the temperature of the CPU. To be able to measure the airspeed produced by the fan flowing through the radiator, we will use an anemometer borrowed by the lab. With the programs installed on the computer and access to an anemometer, we will be able to test fan designs with various number of blades in a well-regulated and well-monitored environment. This next set of photos is a picture of the computer Professor Hoover allowed us to use. On the right, on the left is a picture of the disassembled fan. The main risk associated with this project is the chance for blades spinning at high RPMs to cause cuts or other forms of injuries when not handled properly. To help mitigate this risk, we tried to wear safety glasses and proper laboratory clothing and keep the side panel on the PC on while it was in operation. A low-level risk that is possible but unlikely is the ability for the computer parts to catch fire during our thermal testing. Even though it's a small risk, it is still important for researchers to know where the closest fire extinguisher is and have a control plan for emergency evacuation if needed. There's also a small capital risk in the case that our test fan causes damage to some other components within the computer. To try and lower the potential of this risk of occurring, our team ensured stability of the fan before testing and knew how to shut down if anything sounded dangerous. The main instrument we used for measurement purposes was the Lacrosse Technology Anemometer. It was used to measure airflow through our test fans and has a resolution of plus or minus 0.1 miles per hour. Next, we used an Alienware Aurora R16 desktop with an Intel i7 processor and a NVIDIA 4060 graphics card. The inbuilt control center on this machine was able to monitor the CPU temperature within 1 degree Celsius of accuracy. It also allowed us to set the fan speed on a continuous scale from 20 all the way up to 100%. This fan speed has a resolution of plus or minus 1% as well. A monitor, keyboard, and mouse are also required to view this information. Besides this, we use other common laboratory equipment for filament and installation purposes, such as a hammer, Phillips head screwdriver, Dremel, sandpaper, drill, and hot glue gun. A replacement fan was purchased on Amazon for returning the system to its original state. The same fan that we took out from the computer was used, and it was found on Amazon for $28. And that was the only direct cost for our project. A 3D printer and PLA filament was also used and provided by the lab as well as Colin.
This is an image of our preliminary schedule that we designed for the length of the project being 1 semester. We ran a little behind schedule on some tasks, but overall we stayed fairly close to what was expected. Our first budget suggestion was able to be heavily reduced as we adjusted our scope and were able to utilize the equipment available to us in the lab. Once we finalized our scope, a fan design was created and printing was to commence. Unfortunately, we realized quite late that the fans were backwards and would not work for us. This set us back in a way that was not to our advantage. But once most of the fans were available, we were able to begin testing and gathering data and analyzing the data. Over on the right, we have our budget. Our budget was initially large, but was able to be reduced due to our change in scope, and we were able to utilize the testing equipment as previously said. And our final price, as Corbin just said, was $28.98 for the cost of the fan that we utilized in the computer. And then we had the indirect cost of our PLA, which was about $10. Our test procedure started with the assumption that you have all of your fans ready and printed out. Once you have your fans, you would install the fan hardware into the test blades and then check the fan balance using a handheld drill. This was just to ensure that no damage would immediately be done if you turned on the PC with the fan running. Once the fan was checked for balance, the fan blade was installed in the computer, and the computer was turned on, and the Alienware control center was opened up. Once that was done, the fan speed was incremented up by 20%, and airspeed measurements were taken behind the radiator at each increment. Once you reached 100, the fan blade was set back down, Cinebench was open, and a multi-core test was run to increase the temperature to 69 degrees Celsius. Once reached there, Cinebench was killed, and the fans were run at 100%, and measurements were taken at 30 seconds and 60 seconds. And all of these steps were done for each printed blade iteration.
After testing all of our fans, we were able to tabulate the results and create the graph shown on the left. As expected, blade counts on the very low end or the very high end didn't perform as well as those in the middle of our range. The number of blades that provided the best results were the 7-blade design, the 5-blade design, and the 9-blade design, respectively. Placements of our fans stayed pretty consistent for lower running speeds, and there was a mostly linear relationship between fan speed and volumetric flow rate. The table on the right shows just the maximum flow rates each design reached at 100% of their running speed, and a benchmark is given with respect to the 7-bladed fan, as that was our highest performer. From this table specifically, we're able to notice a particular correlation that is somewhat interesting. Although our dataset isn't large enough to draw a definitive conclusion, it appears that fans with odd number of blades performed better in general. If you look at the results for 6, 8, and 12 compared to their neighbors, you can see this abnormality. Next, we thought it would be useful to see our airflow results as grouped averages for different ranges of blade numbers. For this graph on the left, you can see again how the medium-sized fans performed the best, while fans with too many or too few blades underperformed. From our Cinebench heat dissipation test, we were able to collect the data shown in the graph on the right. With the Alienware Control Center only being able to measure temperature within 1 degree Celsius of accuracy, it was hard to track changes in temperature this small. Most fans in our mid-range had almost the exact same performance, although the largest fans showed worse ability to dissipate the heat. One thing to note for the uncertainty analysis is the resolution of our measuring devices. We measured temperature within plus or minus 1 degree Celsius and airspeed to 0.1 miles per hour. Another thing to note is that due to our time constraints for the project, we were required to spread our 3D prints between different 3D printers, some in the lab and some my personal 3D printer, which all had different filaments, as well as some having different nozzle diameters, and they all had different print setting requirements to guarantee good bed adhesion to give us clean 3D prints. Besides this, there was some uncertainty present from 3D printing issues, especially with the printers in the lab, from bed leveling and some issues that we had with the nozzles in the lab. Some of these fans that we had printed even performed so poorly that they capped out before reaching 100% fan speed and had to be reprinted. This effect can be shown by the one outlier in our data, which is the 6-bladed fan, which performed much worse than expected compared to its neighboring counts, and due to time constraints, we were not able to reprint the fan and get good data. Based on the data collected by the group, we saw that the airspeed output increased as the number of blades increased up to the 9-bladed design before the returns diminished and we started to see a negative relationship. Therefore, we would suggest that the optimal blade number for our design lies between 5 and 9 blades. We believe that the stock fan could potentially be improved for high temperature performance by adding 2 blades. We also saw a slight increase in temperature change over the test minute during the thermal test as blade count increased past 10 blades. The best performing fan for the cooling capacity were the 8 and 9 bladed fans, suggesting this is the optimal level for cooling a radiator. Once again, an interesting correlation we found was that the fans with odd numbers of blades seemed to outperform those with even blade counts in general. We learned that the smaller gap between blades reduces backflow and can increase static pressure, and that too many blades may block its own airflow. While blade count did have a noticeable effect on performance of our fans, we would deem a range of values to be acceptable. This seems to meet our goal. This still meets our goal of determining how many blades should be used on a PC fan and how changing the blade count affects volumetric airflow.
One potential continuation for this project would be to reduce variance in the test fans, for example, by outsourcing our fan designs to a company that can use processes such as injection molding to produce higher quality final products. This would make our products more uniform and have tighter tolerances, and it would allow us to get more accurate test data. We could also measure the power draw from each fan design and see how this changes for the set fan speeds. With the equipment available in the lab, we found it too difficult to measure the isolated power draw of the fan. A singular PC fan has a very low amperage draw, and this is kind of droned out by the power taken by the CPU and GPU in the computer. As our fan is being used to measure heat dissipation across a radiator, it might be useful to test if pulling air or pushing air through the radiator is more beneficial. We could also rerun our tests with a slightly different fan geometry. Finally, we would like to acknowledge Professor Hoover and thank him for allowing us to use the Alienware desktop, as well as giving us access to the tools in the engineering lab. Once again, we're Cooler Kids, and thank you for listening to our project presentation.